Hello everyone, I am Akshay. I'll present our work, Burst Image Restoration and Enhancement. When we take an image, we capture a sampled version of the scene whose quality is limited due to the imaging sensor. Existing single image processing approaches aim to restore and or enhance the image using learned priors. While they can generate natural looking images, they fail to restore details due to the lack of information. Burst photography is a natural solution instead of single frame processing, as it contains multiple images of the scene captured successively. However, during image burst capturing, any movement in camera and or scene objects will cause misalignment issues while merging the information in each frame, thereby leading to ghosting and blurring artifacts in the output. Some of the existing burst image processing approaches does explicit alignment and late fusion, due to which errors caused during the explicit alignment to be propagated to the following stages, thereby negatively affecting the generated outputs. While other approaches use dynamic kernel predictions, which makes the entire network bulky and sometimes faces training instability. Over this, the proposed burst image processing network, we call it as a BIPNet, aligns burst features implicitly followed by interframe communication via pseudo-burst mechanism and adaptive group upsampling. This is the overview of the proposed BIPNet for burst super resolution. BIPNet takes as input a raw image burst and generates high quality RGB image. BIPNet has three key stages: edge boosting feature alignment, pseudo-burst feature fusion, and adaptive group upsampling module. Edge boosting feature alignment module aligns all other images in the input burst to the base frame using modulated deformable convolution and computing high frequency residue as shown here. Feature processing module is added in edge boosting feature alignment to denoise input frames to facilitate the easy alignment. It comprises residual in residual learning empowered by the global context attention. Pseudo-burst is generated by exchanging information across frames such that each feature tensor in pseudo-burst contains complementary properties of all frames. Pseudo-bursts are processed with shared unit to extract multi-scale features. This is our last module, that is adaptive group upsampling, which effectively utilizes the information available in multiple frames to get into HR space. It handles pseudo-burst features in groups and progressively performs upscaling. We sequentially divide the pseudo-burst features into groups of 4. These groups of features are upsampled with the upsampler depicted in figure B, that first computes a dense attention map carrying attention weights for each pixel location. The dense attention maps are then element-wise applied to the respective burst features. We evaluate the proposed BIPNet and other state-of-the-art approaches on real and synthetic datasets for burst super resolution, burst low-light image enhancement, and burst denoising. Our BIPNet is end-to-end trainable and needs no pre-training of any module. For network parameter efficiency, all burst frames are processed with shared BIPNet modules. We train separate model for each task. For burst super resolution, we follow the instructions of the entire 2021 burst super resolution challenge. We use aligned L1 loss to fine-tune the BIPNet for real burst SR track. Our BIPNet achieves noticeable improvement for both synthetic and real tracks in PSNR when compared with existing methods. Also, visual comparison shows that our results are more sharper compared to the existing method. For burst low light image enhancement, we prepare 28,000 burst patches from 161 burst sequences of training split of SID dataset. You can see our BIPNet yields significant performance gain of 3.07 dB over the previous best method on SID dataset. Similarly, the visual examples provided in figure also shows the effectiveness of our approach. For burst image denoising task, we evaluate our BIPNet on grayscale and color burst denoising datasets introduced in recent literature. Following benchmark experimental setup, we utilized 20,000 samples from open images training set to generate synthetic noisy burst. Table shows that our BIPNet significantly advances recent SOTA methods on grayscale burst denoising dataset on all 4 noise levels. On average, BIPNet achieves 2.07 dB improvement over previous base method. While on color burst dataset, our BIPNet provides PSNR boost of 1.34 dB over previous best method. We have released codes and pre-trained models if you would like to try them. Thank you.